Okay, it's 9 a.m. Yeah, 9 a.m. Good morning, everyone. Everything seems to be working, and we can start or continue. So, today, we're going to discuss a few things. First of all, we will revisit a battery, just for a little bit. Then, we will start analyzing simple circuits using Kirchhoff rules. And then, if we still have time, we will start discussing electric power, right? Okay, so first of all, now before we can continue, right, now we need to look at the battery one more time. In terms of have we missed anything in the way we model a work of a battery, right? Okay, so let's bring battery closer to a real life. Right? Of course, you all know that we need a battery in order to create a potential difference, right, and drive a current through a circuit, or currents through a circuit, right, if you have multi-loops. All right, so let's look at a gravitational analog of a battery in order to see what might be missing in the way we model the work of a battery. Right. So, for example, like let's say we have these two slopes, right? Of course, in the gravitational field, right? So we have one slope, then there is a hole over here, right? And there is a second slope. And let me drop a few soccer balls. Of course, I like soccer. Okay, football. Right? All right. So if you drop these soccer balls, of course, there will be sort of a current of these balls, but for 2-3 seconds, and then of course it will stop. All right, this current will disappear. Right? So in order to have a steady current, right? So we need to put here some kind of a device which would move balls from the bottom to the top. I couldn't think of any better device than this guy wearing Brazilian colors, because they're also crazy about soccer, right? All right, so the work of this guy, so he's supposed to grab the ball from the bottom and move it to the top, all right? And of course, we all know that we all have limitations, right? And he cannot move these balls instantaneously. It takes time to grab it, move it, drop it, right? So it takes time. It doesn't matter. Okay, somebody's mic is on. I cannot see who's mic. Because not everyone is shown at the same time on my screen. Okay, I hope the person will realize. Right, so it takes time. So that's why I put the sign, give me a break, I do it as fast as I can. And of course, if you, for example, increase number of balls, again, somebody's mic is on. If you increase
Noel, can you turn your mic off?
Okay, awesome, thank you. Right. So yeah, he give me a break, right? I do it as fast as I can, right? Okay, let me get my thoughts back, right? So actually, yeah. So if you increase number of balls, of course, he wouldn't be able to manage, right? So there will be some sort of like a bottleneck effect over here at the bottom, right? So basically, this sort of like a pump, this device brings natural sort of like a hindrance to otherwise a completely free flow of balls, right? Because he cannot move, device cannot move balls very fast, right? So of course, he brings to the system sort of like an internal resistance, natural hindrance, right? So of course, now the question, how can we model it? Of course, it's not that simple, especially, okay, it's very similar things happens in the battery, right? So because we have two electrodes, and what does a battery do? It just moves electrons from one electrode to the other one. And of course, it takes time to move. It doesn't happen instantaneously. So exactly the same thing happens in a battery, right? So again, the question, how can we model it? Of course, that process in the battery is far from being simple. It's quite complicated. And modeling will be complicated. So what do we usually do in the cases like this? Okay, researchers, physicists, chemists, right? So very often we can sweep it under the rug, right? And cover it with a nice Persian rug. So what do I mean by that? So researchers just introduce the internal resistance. Just a resistance, internal resistance, which is measured experimentally. So all those questions about how can we model, right? We just sweep them under the rug, right? So that's why we need to introduce an internal resistance to our model of a battery, right? So now, as a result, a battery will consist of two kind of parts. The first one, which sort of produces this potential difference, right? Potential difference of an ideal battery. And we use this term EMF, electromotive force. It's a potential difference of an ideal battery. And then the second part, there's internal resistance, right? Don't try to understand what's the meaning of, or even don't try to think what's the meaning of EMF, electromotive force. There's no meaning. It's just a couple of 100 years ago, right, when people work in this hot field, right, hot stuff, right, they had some ideas. So they tried to model what happens in a battery, right? And probably this term was relevant to that model. But with time, that model was completely abandoned because it was wrong. But the name somehow survived. I have no idea why it survived. Maybe just because it sounds cool, right? Electromotive force. Yeah, it's cool. Right. EMF. Okay, so from now on, we're going to use EMF capital epsilon. You see capital epsilon to show that this is a potential difference of an ideal battery. And since you're going to use it to do your homework in mastering physics, this EMF, where can you find this EMF? In a Greek letter box. Open it up, and at the very end there is a capital epsilon. Right? If you put a cursor above that, it will show you EMF. Right? Don't use small epsilon, because mastering physics will tell you that is wrong. So be careful with that, because every semester a few students send me a mail, how come that mastering physics doesn't accept my answer? My answer is correct, right? Yeah, be careful with that. Okay, so now as a result, as I said, we can model the battery in this way, right? So EMF, right, which part of a battery which creates the potential difference, and then internal resistance. Again, usually small letter r is used to denote internal resistance, right? Okay, so now, whenever you try to measure, or whenever you measure potential difference across the battery, so what do you actually measure? You measure EMF and the minus voltage drop across this internal resistance. So what you measure is called the terminal voltage. EMF minus voltage drop across the internal resistor, minus IR. Okay, it's called the terminal voltage. Then, of course, the question is, how can you measure EMF, for example, right? Just EMF. What can we do in order to measure EMF? If you disconnect the load from the battery, let's say maybe there's a resistor or just a complicated circuit. If you disconnect a load from the resistor, then current taking from the battery, which is this current, this I, will be very, very small. Okay, basically it will disappear, right? But of course, if you take a voltmeter with a proper option and connect to this end and that end, of course that voltmeter will still drive a small current, but it will be very, very, very small current. And as a result, your terminal voltage will be very, very close to the value of EMF. For example, if you take a 9-volt battery and try to measure the potential difference across the battery when it is connected to a circuit, then most likely you will measure maybe something like 8.8, maybe 8.9, right? Because there is a voltage drop because of the internal resistance. But if you remove the circuit from the battery and measure with a voltmeter potential difference across the battery, of course it will be very, very close to 9 volts. Right? But if it is connected to the circuit, then of course you will measure the terminal voltage, and there will be voltage drop across an internal resistor. Significant voltage drop, significant voltage drop. So now we introduced EMF, and now we will start using EMF pretty much every class. Right? So now we slightly changed the way we model the battery, and now back to our simple circuits. And so what we've done in the this week, we did not have a lecture right on Tuesday, so we covered new material in our recitation classes. And we introduced the method of an equivalent resistance. Right? And of course, that method has limitations. It can be used only when resistors connected either in series or in parallel. Significant limitations. Tons of circuits where resistors are connected neither in series nor in parallel. So what can be done in that case? And in that case, we can use Kirchhoff's rules, because these rules have no limitations. You can apply them at any time, at any moment, for any circuit. Right? No limitations. And again, we're going to analyze a circuit. So it means what does it mean analyzing a circuit? We're going to look just at a circuit full of resistors and batteries at the very beginning. So it means that we need to find current through each resistor and potential difference across each resistor. Because again, you remember, whenever you want to analyze work of a resistor, you have to look at 3 parameters: resistance, current, and potential difference. Right? Once you know them all, you're all set. But in our problems, resistances will be given, and we will have to every time find current and potential differences. Right, so yeah, I think I mentioned everything, right? Yeah. What is interesting, Kirchhoff mostly known for these rules. And he presented them and stated them when he was still in a graduate school. And then the rest of the life, right? Okay, just wanted to mention that. So let's start stating them. There are two of them, 2 rules. And okay, yeah, I wanted to mention this book, and most of the time we present them as Kirchhoff's laws. But I cannot squeeze out of myself the word law, because for me, laws are something fundamental, universal, right? No limitations, no restrictions. These are applications of fundamental laws. I will state which are those in a circuitry. Applications of fundamental laws, I cannot say that these are laws. Rules, it's my minor compulsion. Okay, anyway, the first one, junction rule. We've already used it, so that's why I'm not opening it piece by piece, because we've used it already several times. You're all familiar. Just basically conservation of current. So if you have any junction point in a circuit, the total amount of currents entering and the total must be equal to the total amount of current leaving a junction point. We've used it already many times, so nothing new. And usually students don't have any troubles with this part of Kirchhoff's rules. And of course, which fundamental law lies behind this? Conservation of charge. Right? Okay, so this is simple. Now, the second one, Kirchhoff's loop rule. Okay, and here we need to practice a little bit and discuss a few things. So, this is the rule. So, if you pick any loop in a circuit, any loop, it doesn't matter which one, and if you start walking in a certain direction, clockwise or counterclockwise, counting potential differences. I want to say voltage drops. No, sometimes voltage can go up, right? If you go, for example, across the battery. And if you count all the potential differences across each element in that loop, When you get back to the origin, to your starting point, you're supposed to end up with 0. All right. Okay. For example, let's say we have this some imaginary loop with 4 elements. You see 4 elements. And very important, every time you will have to pick a certain travel direction. It's a very important. We will practice it, but every time. It doesn't matter which direction. Clockwise, counterclockwise, doesn't matter. Don't think, just pick a direction and follow that direction. And if you start, for example, if you start from this point, let's say this is the starting point, and if you start counting the potential differences, so you'll have delta V1 over here, delta V2, potential difference, delta V3, and delta V4. If you add them all up, you're supposed to end up with 0. Of course, the normal question, what lies behind this rule? As I said, fundamental laws are behind these 2 rules. Behind the first rule, conservation of charge. Can you guess what lies behind this rule? Which fundamental law? Conservation of energy. Let me just justify it quickly. Okay, so here I open it, the whole part. So let's just keep track of one electron, counting or looking at its potential and kinetic energy. So electron starts from here and moves around the loop, right? And it will come back to the same point. And I just want to apply conservation of mechanical energy, right? So of course we usually what? In which way? K initial plus U initial equals to K final plus U final. But if you move all the K's, kinetic energies, to one side and all potential energies to the other side, you will end up with this. So delta K equals to minus delta U. Right? It's just another way of writing conservation of mechanical energy, but I usually prefer to use the other way. But in this case, I think this is better. So when electrons drift, right, with the current, it has on average the same speed. It doesn't matter where you look at that electron, its average speed will be the same. So it means what happens with kinetic energy when it electron moves around the loop and comes back to the same point? It will have exactly the same speed. So it will have exactly the same kinetic energy. If you take the difference, you will end up with 0. So delta K will be 0. It's like if you run around the loop on a stadium, right, with a constant speed. Your initial kinetic energy, let's say 5 joules. When you come back, your kinetic energy will be still 5 joules because your speed is the same. And you didn't lose weight, right? Or maybe you lost weight, right? All right, so in this case, delta K is 0. And as a result, delta U will be equal to 0. And of course, we know the connection between the potential energy and the electric potential, right? U equals QV. So of course, this delta U can be written as Q times delta V. And it is equal to 0. Q, of course, can be dropped, removed, because it is equal to 0. Right? Any constant factor doesn't change. And as a result, what is this delta V? Delta V, it's a potential change when the electron moves around the loop. So it means inside of that delta V, we have this, all this delta V1, delta V2, delta V3, and delta V4. So we're getting this rule. Right. So if you walk around the loop, counting all potential differences, if you add them all up, you're supposed to get 0. Just conservation of mechanical energy. He applied it. Okay, so now we need to spend more time on this rule because we will have to, we need to derive a few rules which we are going to use to count, to calculate these delta V's, right? And we will spend maybe like 10, 15 minutes now developing 4 rules, these 4 rules, which we will use to calculate these potential differences, right? Sort of like a 4 mnemonic rules. It will speed up the process of writing down the equations significantly. Because if you're going to use all those analyses which I'm going to give you now, it will slow you down tremendously, right? Okay, so now we're going to discuss 2 elements, batteries and resistors, right? So we need to develop 2 rules for how we can handle a battery, and 2 rules which will allow us to work with resistors. Right? So overall, 4 mnemonic rules. So let's develop them. Again, it's just for this loop rule. Junction rule, very trivial, right? Okay, so now let's first develop 2 rules for a battery, and then next slide there will be 2 rules for a resistor. Okay, so let's just imagine that we have this battery. So we have negative electrode, you see positive electrode, and as I told you in the previous slide, it's very important every time to pick a travel direction. Let's assume that you pick a travel direction this way. It doesn't matter which direction you pick, clockwise, counterclockwise, it doesn't matter. Don't think, just pick a direction and follow it. But of course, don't tell anyone that I'm telling you don't think. But in this case, it's true. And I will explain why. It's just basically changing a direction. It's like multiplying the equation by -1, the whole equation by -1. The equation will be basically the same, right? So don't think, just pick a certain direction, clockwise, counterclockwise, and follow it. Okay, so let's assume we pick this direction. And now, of course, what are we trying to calculate? We're trying to calculate delta V. And now, of course, I can justify why do we need a travel direction? What's the logic? Why am I forcing you to pick this travel direction all the time? Because we need to know which point is final and which point is initial when you walk across, when you move across the element. If you don't have travel direction, you don't know which point is final and which point is initial, because delta V, it's a V final minus V initial. So in this case, once we pick a direction, okay, so this is our final point, right? Because we started here and then we ended up there. And this is our initial point, right? So that's why we need a travel direction, so that we know which point is final and which point is initial when you move across the element, in this case across a battery. That's why every time we need to pick a direction. Which one, it doesn't matter. But it must be the same for the same loop, right? Okay, so now, next, which point is at higher potential, initial or final? Because we need to analyze this. We know the properties of the battery, right? So this is the positive electrode, so it is at higher potential. Negative electrode is, of course, at lower potential because the potential is negative, right? So using properties of the battery, we can tell immediately that this point is at higher potential, which is the final point, and this point on this side, which is the initial point, is at a lower potential, because we see the circuit, we see that this electrode is positive, that electrode is negative. Right. So it means that I can write over here, V final, this is final point, is at higher potential, so it's basically V plus minus V minus. Again, plus it means higher potential, minus means low potential. So as a result, what will be delta V? Is delta V positive or negative? Of course positive, because we're subtracting a larger number from a smaller number. Oh yeah, subtracting smaller number from a larger number, right? Of course you will end up with positive value. And so this is, we assume that this is an ideal battery. And which symbol do we use to show the potential difference across an ideal battery? EMF, right? EMF. If you have an internal resistance in the battery, of course, you can treat it as a resistor, and the resistors will be discussed in the next slide. So the potential difference, of course, is positive, and of course, we can state the rule, right? So potential difference across the battery is plus EMF if you travel from the negative electrode to positive electrode. So mnemonic rule number 1. If you travel from the negative electrode to the positive electrode of a battery, contribution to that loop equation will be plus EMF. We're going to practice, right? So we're going to practice on the whiteboard, right? Okay, so the rule number one. Now, reverse situation. What if you travel from plus to minus? Of course, you can tell immediately that the contribution will be negative, minus EMF. But anyway, let's just quickly discuss that situation. Again, so now I just flip the battery, right? You see here we have a plus over there, minus here. Now we have plus here, minus there. And the travel direction. But now you see we're traveling from plus to minus, not from minus to plus like over there. Of course, now again, according to the travel direction, this is final point, this is initial point, and of course now our final point is negative electrode, so the electric potential is lower. And of course, initial point is plus higher potential. So of course now if you subtract V final minus V initial, so it's a final lower, V minus minus V plus. So contribution to the equation, to the loop equation, is going to be negative, minus EMF, electromotive force. Okay, I don't want to block. No problem, I'll move to this side. It's better. Right. Okay, so mnemonic rule number two. If you travel from plus to minus, contribution is negative. Okay, so that's about batteries. That's how we can handle a battery. Now, two rules about resistors. With the resistor, slightly more complicated situation, but not that complicated. Okay, I guess I can move to the next one. Okay, so now resistors. Here is one. Right? Of course, resistance is given. And again, it's a part of the loop. Of course, every time before we start analyzing a loop, again, we pick a direction, travel direction, clockwise or counterclockwise, whatever you prefer. Let's assume that we pick this direction. Of course, now we know why we need it, because we need to know which point is final. In this case, this is, okay, this is initial, and this is final point. And now if I ask you, do we know which side of the battery is at higher potential and which side is at the, oh, not battery, resistor, sorry, resistor, right, is at higher potential, electric potential, and which side is at lower? Sometimes students give me a sort of direct answer, so this point is at higher potential, that point is at lower potential. I cannot tell, because right now we just don't have any information about that. On the previous slide, when we were discussing batteries, yeah, by looking at the batteries, because we know that longer bar represents positive electrodes, shorter bar negative electrodes, so we knew this point is at higher potential, this point is at low potential. Now I have no idea. I cannot tell if this side is at higher potential or this at higher potential or this at lower or that at lower. We just don't have that information. So in order to sort of overcome this obstacle, in order to move forward, let's assume a second direction, a current direction. Every time we will be picking two directions. One, travel, and now let's assume a current direction. Again, you can say, come on, what does it mean, assume, right? There's a certain direction, all right, but we have 50% chances of getting it right. You remember? I used these arguments, I think, in the previous lecture, right? Current flows either this way or that way. From a gambling point of view, it's a huge percentage. 50%. Huge. So let's use it. So if I assume my current direction, for example, that way, and using that assumption, I solve the problem. I find the values of the current. Every time we will have to find current, right? And find the value of the current. And if my current, this current, happens to be positive, okay, I'm good at gambling, right? It means that my assumption about current direction was correct. And the number of the value of the current I calculated. But if your current happens to be negative, let's say minus 5 amps, okay, I see the value of the current, 5 amps, and minus would just mean that, okay, I'm bad at gambling. I didn't, my assumption was wrong. So just make a statement. So actual direction of the current is in the opposite direction. But you solve the problem. Who cares if you're a good gambler or bad gambler? You solve the problem, right? And once, if you know now, if you assume the current direction, now can you tell me which side or which point is at higher potential and which point is at lower potential? This is higher or that is higher? You remember current flows what? From plus to minus. From positive electrode of the battery to a negative electrode of the battery, right? So basically current every time flows from the regions with higher potential to the regions with lower potential. So if we assume this current direction, then immediately it means that according to that assumption, this side must be at higher potential, because again, current flows from plus to minus. So basically this is plus and that is minus. So this will be at lower potential. So basically we have to assume every time current direction in order to make a decision which point is at higher potential and which point will be at the lower potential. Again, in our gambling game. All right? So that's why I told you that dealing with resistors is slightly more complicated. So when we analyzed batteries, we didn't need current direction. We just needed travel direction. But in order to work with a resistor, we need two directions. Every time we will have to assume travel direction and then current direction. And in both cases, it doesn't matter which direction. Because very often you have a multi-loop circuit and there's just no way to tell which direction, which current direction is correct one. No way, it's too complicated. So every time we will just assume, let's assume this is current direction or that is a current direction. And then when you solve the problem, we start making a statement and adjustments. Okay, current positive, my guessing was correct. Current is negative, okay, my guessing about current direction was wrong. Change it. You solve the problem. You are the winner, right? So now on these preliminary steps, and now again, what do we want? We want to calculate delta V, potential difference across this element, across this resistor. So delta V, again, final minus initial, V final minus V initial. So this is the final point, and you see our final point is at the lower potential. So this is V minus, and initial point, that the initial point is over here, right? The initial point is at higher potential. So this is V plus. So as a result, I can write V minus minus V plus. So we subtract larger number from the smaller number. Positive or negative? Of course, negative. And all right, every time resistance will be given, and we need to find current. And we need to find current. All right. So how can we write this delta V if you want to find current? That's your unknown and resistance is given. Ohm's law, IR. So minus IR. So that's the contribution to our loop equation. So now mnemonic rule number 3. The first two about batteries. Now the first rule about a resistor. If current direction and travel directions are the same, in the same direction, contribution is minus IR. We're going to practice it. I will remove the green screen and we'll start writing on the board. And of course, now the last rule. What if these directions are opposite? And of course, you can guess immediately what will be the answer, right? You can run similar analysis, but let's do it. So again, resistor, you assume a direction. Let's travel direction that way. And now let's assume that you pick current direction that way. Okay, so now this is at higher potential because again, you remember current flows from plus to minus, from regions with higher potentials to the regions with lower potential. So this is plus, this is minus, right? So final point is this, right? Which is at higher potential, and this is the initial point, which is at lower potential. So in this case, V plus minus V minus, so contribution must be positive. And we know how we can write it, IR, but in this case, plus IR. So if directions, current and travel directions are opposite, contribution is positive. Right? Okay, of course you can say, okay, you know what, you created these stupid rules, I hate them, right, with all my heart, right, I don't want to use them. Okay, your choice, why not? But in that case, you will have to run this analysis every time. And trust me, after a couple of reasonably simple problems, you will hate everything around yourself, right? Because it's so tedious, right? Running this analysis, this higher potential, lower potential, this is final point, this is initial point, it will slow you down tremendously. And sooner or later, after a couple of problems, you'll start developing maybe your own mnemonic rules. And they will be somewhat similar, maybe slightly different, but okay, develop your own rules and use them. And then once you practice a few times, right, using your own rules or these rules, the process of writing loop equation becomes trivial. It's very simple, right? The same direction, positive contribution, or negative contribution, opposite directions, negative contribution, right? I know, opposite direction, positive contribution. Better from minus to plus, it's a plus EMF, from plus to minus, minus EMF, right? So if you practice a few times, it's easy to remember these rules, right? They're quite simple. And writing equations becomes like within 20 seconds you can write the equation. Okay, so now I think now it's time for me to look at the example. Let me check quickly. Yeah, that's what I just told you. And yeah, this example I will skip. It's just one loop. All right, it's not a big deal, right? Let's look at two loop example. Okay, so if you don't have any objections or questions, let me switch to the whiteboard. I prepared this picture to save a couple of seconds. And so the question is, we need to analyze this circuit. Now it's a multi-loop circuit, okay, two-loop circuit. We have two batteries and three resistors. We need to analyze it. What does it mean, analyzing? Analyzing means we need to know everything about each of these elements. We assume that those are ideal batteries. EMFs are given, so you know everything about battery. And we have three resistors. Resistances are given, so we need to find currents through each of these resistors and potential differences. Right. Okay, once you know all that, you know everything about the circuit. And of course, none of these resistors are connected either in series or in parallel. Although they look like a parallel, but this junction point ruins everything, right? So none of them connected in series or in parallel. So it means that we cannot use method of an equivalent resistance, so we have to use Kirchhoff rules, right? Kirchhoff rules. All right, and before we start applying them, we have to make sort of identified three preliminary steps. Which are those? Right. So first of all, we need to identify junction points. It's very important. Right. So let me write. Maybe I will move a little bit. So preliminary steps. Preliminary steps, sort of like a preparation. First one, identify junction points. Okay, in our case, there are two junction points. Let me label this one as, for example, A, and this is B. So two junction points. So in our case, A and B. Then, what happens at a junction point? Current gets split or currents merge, right? So it means that if we, for example, look at this part of the circuit between point A and B, but this part, slightly erased it, right? So this part of the circuit, this branch, there are no any junction points. Again, between A and B in this part of the circuit, there are no any junction points, right? So it means that current stays the same. Current stays the same. Okay, if current stays the same in this part of the circuit, let's label it and choose a direction. Do you remember? In order to analyze, and we have here a resistor, in order to analyze a resistor, we have to assume current directions. Which way? This way or that way? I have no idea. We have a battle of two batteries. So what will be direction of current? I have no idea. I would never even dare to guess. Maybe people from EE department, right, with lots of experience, maybe they can, although I doubt, right? So let's assume that, okay, I will follow my notes, right? So direction, my direction is this way. So my direction of the current, so this is I1. So again, I1 between point A and point B in this part. Again, you could have picked this direction. Nothing wrong with that. Don't think about directions in this problem, in this type of problems. Just pick a direction, solve the problem, and then at the end, you will adjust it if it's needed. Okay, so the first current. Now, this part of the circuit between points A and B, again, there are no junction points in this part, so it means that current must be the same. Again, let's label it I2. Again, direction up or down, it doesn't matter. Pick any. Which direction I pick? I picked up. Okay, so let me pick. So this is my I2. Again, between points A and B. Right? At this point, yeah, current changes. And then we have this part. Again, between point A and B, over here, there are no any junction points. It means that current stays the same. So let's give it a name, I3. And direction, it doesn't matter. This way or that way, I have no idea, right? I'll just look at my notes. I picked this way, right? I picked this way. So that's our current I3. Again, between points A and B. Usually, the only thing I prefer, if I have a junction point, at least, I don't know, if two currents enter, one must leave, right? Or if one enters, two must leave, right? So I just try to do that, right? Because I know that all currents cannot just enter with the same junction point. All currents leave a junction point, right? It's not a big deal. You will definitely get some currents being negative, right? 100% in that case, if you pick all currents entering or all currents leaving the junction point. Okay, so now second preliminary step. So choose currents and directions, and And again, any direction. So choose currents and or label currents and choose directions. And the last preliminary step, what else do we need? We need traveling directions, right, for each loop. Okay, in this case, we are going to use this loop and that loop. Of course, there is also external loop, but I will make a statement at the end of this problem about the external loop. This loop and that loop is enough. Right. So, okay, this let's label loop number 1. In travel direction, again, it doesn't matter which direction, clockwise or counterclockwise. Again, as I said, the difference between this direction and that direction in the equation which we are going to write is just like multiplying the whole equation by -1. It's just changing the signs next to each term. Equations will be still the same, right? So that's why which direction I pick? I picked counterclockwise. Okay, let me use green. So that will be loop 1. That's the travel direction. Loop 1, travel. And let me pick also over here in the loop 2. So this is loop 2, and that's our travel direction, right? Okay, and after this, we are ready to start writing equations. First, you need to, yeah, I didn't write the third. So, travel directions. Travel directions. Again, any. Clockwise, counterclockwise, it doesn't matter. You know what? Yeah, whenever you solve problem like this, you have tons of freedom to choose any current direction or choose any travel directions. But you know what? When I started teaching this course, right, and one of my exams, I gave a problem like this, and I gave students complete freedom. They could choose any directions, right? Okay, they solved the exam, right? So we collected exam papers, right? And I assigned my TA to grade that problem. He grabbed all the envelopes, went to his cubicle, right? In half an hour, he came back saying, "Kill me." You know why? Because now he had to sit and check. All students picked all the possible directions, right? And he had to sit and carefully check each term. Okay, this is the direction this way, current direction travel this way, so is it plus, minus, right? It's a ridiculous amount of work, right? So yeah, I realized that it was very stupid of me to give that freedom. So of course, when I finished grading my problem, I helped, right, I helped TA to grade that problem, right, because it was my fault, right? So from now on, whenever I give a problem like this, I give all current directions and all travel directions, because otherwise grading becomes, it's a nightmare. It's a nightmare, right? Okay, so, but of course, you have freedom to choose any directions. But whenever I give it on the exam, no freedom. All right. Okay, so let's start with first junction rule. Junction rule, which is the total, all the currents, the total amount of current entering must be equal to the total amount of current leaving a junction point, right? So that's junction rule. And how many junction points? We have two, A and B. A, junction point A. Okay? In, all currents in. So what do we have? I2 in and I3 in, right? You see, this current enters and this current enters, right? So we will have I2 plus I3 and leaves out only one current, this I1, right? You see, it leaves. So equals to I1. Okay, equation number one. Now the second junction point. B. So now in I1 and out I2 and I3. What's the difference between these two equations? There are no any differences, right? They're identical, right? Of course, in the fancy words, we can say they're linearly dependent. But basically, we can say one of them is redundant. So we can remove it because it doesn't give us any additional information, right? So I will just dump this so, and I will write redundant. And a rule in general, if your circuit has n junction points, then you will have only n minus 1 useful junction equations. In this case, n equals 2. And as a result, n minus 1, we have, All right, it's almost over. We have n minus 1 useful junction equations, right? So this is, as a result, we have only one equation, right? Okay, guys, right? I thought I will be able to finish, right, this, right, problem. So this material is not on this homework, which is due Sunday, not, right? So I guess yeah, we will finish this example on Tuesday, right? We will finish this example on Tuesday. Okay, it's just 5 minutes, extra minutes. I just needed to finish it, right? And somewhere I moved a little bit slower than I was planning. Okay, guys, right? So that's it, right? And I'll see you next week.